All right, so today we're looking at lesson 53. We're going to look at equivalent resistance. So hopefully after this lesson you'll understand equivalent resistance. We're going to start off by looking at this circuit. They show us a resistor and labeled R right here. And it's connected to a 30-volt DC, and that stands for direct current power supply. And that's over here. Okay? So we start off with that picture there. And then it says that the current that flows into the circuit is going to depend on the resistance of the resistor R. Okay? So whatever the resistance R here, that is going to determine what the current that flows into the circuit will be. So if we look at these three pictures, if our R is a 1, like in the picture on the left, then the current is going to be 30 amps. If the R is a 5 ohm, like here, then the current will be 6 amps. And then if the R is a 10, then the current will be 3. Remember that your volts equals the times the R. So 1 times 30 is 30, 5 times 6 is 30, and then 10 times 3 is 30. So the current is going to adjust itself so that the product of the current and the resistance is 30. We're using that same formula here. So depending on what this is, your current is going to adjust so that when you multiply those, you get your voltage, which is 30. So the algebraic sum of the volts around a closed loop is always going to be 0. Algebraic sum of the voltages around the closed loop is always going to be 0. The voltage at the output of a real power supply is going to decrease as the current increases. So if you have a real power supply, as your voltage as your current increases, your voltage is going to have to decrease. So it says in the book that good power supplies are rather expensive, but they can maintain an output voltage that is almost consistent for a wide range of currents. So catalogs will list power supplies whose output voltage decreases from 5 volts to only 4.9 volts as the current increases from 0 to 300 amps. So it will decrease slightly in real life, but only by a little bit. But in this book, we're going to assume that all power supplies are perfect and will supply any current demanded without a reduction in the output voltage. So in real life, as your current increases, the voltage will decrease. But in this book, we're going to assume that there is no change, just to make it a little bit easier. Okay? So an electric circuit connected so that all the current passes through each circuit element in turn is called a series circuit. And so I've got a picture. The circuit on the left is a series circuit, and the resistors are said to be connected in series. Often, whenever we have circuit analysis, it's going to be convenient to just replace the 3 resistors that we have, or however many it is in the picture that you're given, with just 1 resistor, and it'll still have the same current to flow. It just makes it a little bit easier. So on the picture on the left, we've got 3 resistors, 5, 4, and 6. And if you combine those, that's 15. And so we can make 1 resistor over here, which is of a 15. And it's the same one, it just makes your picture a little bit easier. Your circuit's going to be a little bit easier to work with. Okay? Often in circuit analysis, it is convenient to be able to replace several resistors with a single resistor that would cause the same current to flow. So that's what we just did. We took those 3 on the left and made it into 1 on the right. The equivalent resistance of resistors in series equals the sum of the individual resistances. So on the last one, we only had 3, so we wouldn't have these over here. We had a 5 and a 4, and a 6. And if you add those together, the total is 15. So that's what we did on that example. But that's all you would do. Just add up the individual ones to find the total. Okay, looking at this one. In the circuit on the left, the voltage across the resistors is 30. The voltage is 30. They tell us that in the picture. These resistors are said to be connected in parallel because some of the incoming current passes through one resistor and the rest takes a parallel journey through the other resistor. So these are said to be in parallel. Do you see how they are parallel? The 10 and the 15 here, they're on parallel lines. Okay? And so the way that you work with those, on the right side, we're going to replace the 2 parallel resistors with a 6. And now you didn't add those 10 and 15 together. You didn't subtract them. The way that you figure that out, if you look here at the 15 resistor and the 2, the amp, the current is 2. And over here, if you look at this resistor, the current is 3. And so the new current over here, this I, has to be a total of a 5. So that's what we put here, a 5. And so if this is a 5, then that means that for our resistor, if we're going to have a voltage of 30, it's going to have to be a 6, because 6 times 5 is going to give us a 30. So when we look at our current 2 and our current 3, we have a total current of 5 in this picture. The current total is 5. And so we still have a current total over here of 5, so that means that our resistor, if we're going to make it into 1, is going to be a 6. Okay, so that's how that works. The reciprocal of the equivalent resistance of resistors in parallel is going to equal the sum of the reciprocals of the individual resistances. So on the last one, we only had 2 resistors on the left. We had a 15 and a 10, so we have 1 over 15, and we have 1 over 10. And if you add those together, well, we can make a common denominator of 30. So that would be 2 over 30 and 3 over 30. And that would be 5 over 30, which is 1/6. And if you remember the picture on the left, I'm going to go back. I mean, the picture on the right. I'm sorry. The picture on the right, the current is 6 here. And so the reciprocal of that is 1 over 6. And so that's how you can kind of check with your parallel ones. So if they're parallel, you have to use reciprocals. Okay? So let's look at an example. We want to replace the parallel resistors with an equivalent resistance. And then we want to combine this resistance with the 2 ohm resistor. And then we want to find our I. Okay, so first we're going to have to use the parallel resistors to find the equivalent resistance. And so we have 2 that are in parallel. We've got the 4 and the 6. So to find the equivalent one, we're going to use the reciprocals. So 1 over the equivalent one is going to be 1 over 4 plus 1 over 6. And so you're going to add those 2 together. Those have a common denominator of a 12. So this can be 3 over 12 plus 2 over 12, which is 5 over 12. And then we want to find RE. And so you can, since we have one fraction on each side, we can just take the reciprocal of both sides. So the reciprocal of this is going to be R sub E. And the reciprocal of 5 over 12 is 12 over 5. But we don't deal with fractions in physics, so we make it into a decimal, 2.4. But we have 3 sig figs, so we need to add a 0. And then the units is your ohm. So that's the equivalent resistor. So now our picture doesn't have this part over here. it has a 2.40 resistor there. And so then we want to combine those two. So if we combine them, we end up with 4.40 ohms. If we combine this 2 and this 2.4, that's what we end up with, 4.4. And so now we're going to use our formula, voltage equals IR. Our voltage is 20. We are looking for the I, the current, and then our resistor is 4.40. And so if you do 20 divided by 4.4, you end up with 4.5454 repeating. And so we have 3 sig figs, so 4.55 amps would be your I. Okay, so that's how you deal with parallel resistors and also then combining resistors in series. Looking at another example, we have a current through the 4 ohm resistor is 3 amps, and then we want to find the current through the 6 ohm resistor. Alright, so if you look at this first resistor right here, we have 3 amps and we have 4 for the resistor, so that means that the voltage here is 12 volts. We have a positive here and then a negative on that side. The total of our system was 24, but 12 of them are dropped off here. So that means that we have another 12 volts to be used in this part of our circuit. Both of our parallel resistors are going to have 12 volts total. Okay? And so we know that we start with, we're going to start here. We're going to have a negative 24, and then we have a positive 12, and then we have to have another positive 12 to make that equal 0. That's how we figured out that it was 12, if you want to do it the long way. Or you can just say we started with 24, we lost 12, so we have another 12 to use. So the current through these is what we need to figure out. We know that our voltage equals IR. Our voltage is 12. We don't know the current, but we know that the resistor, we have this resistor here, 6. So the current is going to be 2 here. And that was what they were asking us to find. Find the current through the 6 ohm resistor. We have 3 amps in total. 2 of them come through here. So that means that one more, one more has to come through here. Or we could actually do it mathematically using our formula. Our voltage is 12, our current we don't know, and our resistor is 12. And so your I would have to be 1. So that's using the formula, but once you find one, you could find the other one. They only ask you for this one though. Find the current through the 6 ohm resistor. So that's how those work. If you are interested in looking at a proof for what we looked at today in the lesson, check out page 366 and 367 in the book, and they kind of walk through a little bit of a proof there. So anyway, I hope that helps you with equivalent resistances. I don't think they're terribly hard, but you just have to know a little bit about circuits to be able to work with them. So your homework is 1 through 20, and the curveball questions 1 through 5. So make sure that y'all do those tonight so that we can go over any questions you have tomorrow.